Hi everyone. Today I'm going to run through the Felkin-Anh model, arguably one of the cornerstones of diastereoselective synthesis in organic chemistry. I'll run through the origins of the model and the requirements on any reaction, and also show a particularly effective use of it in natural product synthesis at the end. If you find the video useful, please do give it a like and consider subscribing to my channel. It really helps me plan out my future videos. Right then, to start with, we need to think about carbonyl additions, and in particular, I want to think about aldehydes and ketones of this form, with two different R groups, R1 and R2. When I attack that with a nucleophile and then do an acid workup afterwards, I'll get an alcohol product. And at the same time, I form a new stereocentre. Now, if there's nothing special about R1 and R2, I'll get a 50-50 mixture of configurations at that stereocentre. And by configuration, I mean just the R or the S form, for example. So what I'm saying is that this is equivalent to a one-to-one mixture of these two configurations. And that's because that carbonyl group is equally likely to have been attacked from the front or the back. And if I just draw it on its side, what we're really doing here is attacking into the pi star at an angle of 107 degrees. This is the so-called Burgi-Dunitz trajectory. And because that pi star is symmetrical on the top or bottom face of the carbonyl, there's nothing to favor one side of attack or the other. However, there is a special case where we can get a preference for one face to be attacked over the other. And that's when you have an alpha stereocentre. So that's the stereocentre right next to the carbonyl on one of the groups. And specifically, that alpha stereocentre has to have three distinct functional groups. And by distinct, this is often on sterics, by which I mean you have an R large, an R medium, and an R small as our three different groups. In a lot of cases, the R small is a hydrogen. Now, why is this important? Well, I'll just draw out what I mean by a compound that looks like this. I'm just going to change my R1 into having three groups, an R large, an R medium, and an R small, just with L, M, and S as subscripts. And just to help keep track of things, I'm just going to use an example of an aldehyde here, so that I don't have too many things called R. But this argument will work equally well for ketones too. Now, the point is that this bond here around this CC has restricted rotation, and that might not be obvious at a first glance. And it's a lot easier to see if we take a viewpoint just looking down this bond here. I'm just going to draw it as a Newman projection because that's my favorite way of looking at these things. So that's looking down the plane of the carbonyl bond here. And around the back, we'll just have three different groups. I'm just going to put some blobs on there for now. And these can sit in lots of different positions. So molecules sit in lots of different conformations, and we need to look at what happens in this particular circumstance. So I can put my different R groups in for these blobs. And the first thing I notice is there will be some energy maxima, some conformations that definitely won't be favorable to be in, and they're ones with eclipsing interactions. So for example, if I were to eclipse one of the blobs with the hydrogen, there would be a bad steric clash down here. But also, it would be bad if I put one of the blobs eclipsing the carbonyl group. So just tucking one of them behind there, we could get a clash here. So these are not favorable conformations. And now just having a think about what the most favorable conformations would be, these would be the most populated conformers. Well, they're going to be the ones where you put the R large in as much empty space as possible. And in this scenario, that's when you put it at 90 degrees to the carbonyl plane like this. By default, that's going to put the two other groups in these positions. So for example, we could have R medium up here or R small down the bottom. There is, of course, two ways of doing this. So I can just rotate this round by 180 degrees to get me another favored conformer. So that's my carbonyl plane just staying as it is. And I'm going to rotate the blue bit around the back to put R large on the left-hand side in its empty space. That rotation is going to put R small in this position and R medium down the bottom here. So these are the two most populated conformers. They're the energy minima for the rotation around that CC bond. I'm just going to label them conformer 1 and conformer 2. Now, the basis of the Felkin-Anh model is to exploit the fact that these two conformations are preferred. Now, I'll say at this point that there are other models that are out there for explaining diastereoselective addition to carbonyl groups. However, at the time of making this video, the one that has stood the test of time the best is the Felkin-Anh model, in that it's the most highly predictive of the models that were proposed in the last century, and therefore it should be the key one that you know about. There's a key requirement for the Felkin-Anh model that sometimes gets forgotten about, and that's that it requires kinetic control. So just to be clear what I mean by that, you need an irreversible attack of a nucleophile if you use a nucleophile that can reverse, you can just go in and out and then pick the thermodynamic product overall. That's not what we're going to talk about here. And the point is, if we have an irreversible attack of a nucleophile, we have to react in the way that is easiest. And in chemistry, what we mean by that is the pathway that has the lowest activation energy. So the easiest reactions to occur will be using those most populated conformations. Now I'm just going to draw those favorable conformations out again. And we can remember we've got some rotation going on. So these are interchangeable. I'm just going to use an equilibrium arrow to represent that. So now to work out what the easiest attack trajectory is, we notice that there's two populated conformers, each of which has a pi star. You can attack a carbonyl group from two sides. So there's 4 trajectories in total to have a think about. So just attacking conformer 1. This one could attack on the left-hand side like this orange line, or on the right-hand side like this one. This is attacking at 107 degrees. That's the Burgi-Dunitz trajectory. And we can have a look at conformer 2 as well and draw in the trajectories the same on the left and on the right. So we can quite quickly spot some of the harder trajectories for the nucleophile. The R large group is sterically the most problematic group, and it's getting in the way. So we can quickly discount attacking near to that R large just on steric grounds. That leaves us 2 remaining attack trajectories, one on each of the conformers. And we can see on conformer 1, we're attacking across the small group, and that's just going to be easier than attacking over the medium group. Now, it's not really, we can't attack over the medium one. It's just that attacking over R small is faster. And when we're under kinetic control, that's what we're looking for. I'm just going to stay with my Newman projection here, just keeping the back the same. We'll see that we can get attack of the nucleophile on the left-hand side here to give me a molecule that looks like this. Then I'll do an acid workup to give me an alcohol. Now I just want to keep an eye on the stereochemistry here. The way I normally do this is I draw a line on my Newman projection like this to show that I want to keep my nucleophile and my R large in the same plane. Then I can draw R large, going to nucleophile. And I can see that my newly formed hydroxyl group is on the same side as the R medium. So in this particular case, my R small and my R medium are this way round. And I've just got my yellow plane here and as a zigzag. My R medium is on the same side, so that's down for the hydroxyl group and forwards for the hydrogen. So this particular molecule is formed in good DR. You can notice it has 2 stereocentres. So this is a diastereoselective reaction. That means that we've selected one diastereomer in preference, but the reaction mechanism in principle could form the other diastereomer. The other diastereomer will come from reaction down the bottom here on conformer 2. Now, there's an important thing to remember about the Felkin-Anh model, in that there's a modification if one of the groups happens to be an electronegative atom. This modification is sometimes known as the polar Felkin-Anh model. Now, the way that this is often quoted is that the electronegative atom acts as if it's R large. And I thought I should explain where this comes from, because at first glance, this should seem quite strange. I'm going to use an example of a molecule where this will be manifested, specifically this aldehyde here, where I have a phenyl group which is sterically the largest, but also I have an oxygen on one of the groups, which is an electronegative atom. So just to follow through from where we were on the previous page, these two are still the most populated conformations, where the phenyl group is sterically the biggest group. But to go forward in explaining the experimental observations, we're going to need to think about the conformations where the OME is in the perpendicular position. And we still have rotation about those, so these are just still equilibrium arrows. One way that I can do that on the left-hand side is just to pull the OME down a little bit and send everything round in an anti-clockwise fashion like this. It's keeping the carbonyl as it was, the OME can go into this perpendicular position. And that's going to send the phenyl group up here and the hydrogen down here. On the right-hand side, I can do exactly the same thing. I'm just going to move the OME up a little bit and move the other groups round and move round in an anti-clockwise fashion again. This will put the OME here in a different perpendicular position, leave me with the hydrogen and the phenyl group like this. And these two, of course, are in equilibrium as well. So just to write a note, these are the conformations where the electronegative atom is in the perpendicular position. Now, it turns out that in contrast to these ones in blue, which are the most populated conformations, these ones in purple down the bottom here are the most reactive to nucleophilic attack. And to explain that, we're going to need to think about the orbitals involved. We're overturning a steric argument here often the way that that happens is when we have an electronic argument fighting against it. This is to do with the CO bond. So that's a new CO bond attached to the OMe. I can draw a quick molecular orbital diagram to show that if I bond carbon to oxygen, well, oxygen is more electronegative, there'll be a lower energy orbital than the carbon. So when I form any interaction between them, so in particular here a sigma interaction, I form a sigma bond, which I can put my electrons into, and a sigma star, the antibonding orbital. And what we can see is because there was such a big difference between the carbon and the oxygen, this overlap is not particularly efficient. So this sigma star is pretty low in energy for a sigma star orbital. We can see that the energy mismatch has only pushed the sigma bond down a little bit relative to the oxygen, and so the sigma star pushes up a little bit by roughly the same amount. So actually specifically a CO sigma star is actually potentially a better match for other orbitals that we wouldn't necessarily expect. One of the big differences here is if we compare the CO sigma star to say some other common sigma stars like the CC or the CH, the CC and CH sigma stars are way higher in energy and tend to not get in the way of whatever's going on with the HOMO-LUMO interactions in the mechanism. I'll also just highlight here that this is the same for any electronegative atom, pretty much by definition of what electronegative means. Now, an important consequence of this is that when the CO bond is in the perpendicular conformation, the low energy CO sigma star is perfectly aligned to the carbonyl pi star, which is the LUMO for the reaction. I'm just going to draw the molecule in 3D just to emphasize the overlap that I'm talking about. So I'm just going to put the carbonyl on its side like this, put the hydrogen out to the back of the aldehyde, and put the alpha stereocentre coming forwards. If I put the MEO in the perpendicular position like this, that will leave me two other positions. I can see that the LUMO, the pi star, is now well lined up with the sigma star, which looks like this. And if we have orbitals of similar symmetry, size, and importantly, energy here, they must interact. That's a fundamental concept in molecular orbital theory. So that means in this particular conformation, the CO sigma star must be overlapping with the CO pi star LUMO to form a new combined molecular orbital like this. Now it looks a bit strange here because both of these orbitals are empty, but this one at the bottom is now lower in energy. It's lower in energy than the original carbonyl pi star, therefore it's easier to be attacked by a nucleophile. Therefore it's a better match to the HOMO of a nucleophile. Therefore reaction with this conformation will be faster. Now just to map this picture back to the original conformations on the left-hand side, this 3D arrangement here, where I'm just going to put a green star by it, is actually the very same one that we had over on the left-hand side, one of the purple conformations. In fact, this first one over here that I've put a green star on as well. And looking at all the possible attack trajectories onto those purple reactive conformations, we can quickly see that the most preferred one will be attack of a nucleophile, as I've indicated here with the arrow. This one is flying past the small group. That will be the easiest of the options for the reactive purple conformations. And we can just have a look at what the product will be here. Just going to keep the back the same. And I've got attack from the nucleophile from the right, leaving my hydrogens and an alcohol. So that's after an acidic workup as well. I can just draw my yellow line across the middle to check what my products are. So this time I've got MEO in the same plane as the nucleophile. I can see that my hydroxyl is on the same side as the phenyl group, and that will give me this product here. And I can quickly just map this onto the one that I had before by rotating around this bond and putting the phenyl group into the plane of the paper. And in this conformation, we can see that the OMe and the OH are anti to each other. And if you compare back to the previous page where we were only considering sterics, you would see that this is the opposite of what the model would have predicted. However, this is the product that you'll form in the highest DR. Now, there are a few more things we need to be aware of if we're going to use this model in practice. And unfortunately, there is a modification to the modification we just talked about. And that is that a chelating metal can overturn the diastereoselectivity of the polar Felkin-Anh model. So just to be clear what we mean here, if we happen to have a cation in there with a highest charge density, and common ones we might come across in organic chemistry are magnesium 2+, zinc 2+, titanium 4+, maybe. There's lots of others. These chelating metal ions can stick to our electronegative atoms. To be clear, things that don't tend to chelate in these situations are things like sodium plus and potassium plus. Notice the low +1 charge. Lithium plus, well, which we often see in organic chemistry, usually doesn't chelate, but is quite dependent on the reaction conditions. And what I mean by that is normally the solvent and any additives that you have. Well, what's going on here? Well, let's just take our example from last time with my phenol group, my OMe group, and the hydrogen on my alpha stereocentre. We said the most reactive conformation is this one which has the OMe in the perpendicular position. But if you have a chelating metal in there, like magnesium, well, there's a couple of lone pairs kicking around quite near each other, and the magnesium can stick to both of them. And this has quite an important impact on the different reactivity of things. For one, when it's coordinated, that will activate the carbonyl and make the carbonyl more electrophilic when the magnesium is stuck on than when it's not. But also, it affects the sterics of the situation when you have the magnesium present, in that it pulls the OMe group into the eclipsing position behind the carbonyl. This has the consequence of moving the other groups around, of course. So by moving the OMe upwards, the phenol group has to move around and the hydrogen has to move around at the back, just indicated by these orange arrows. This setup is sometimes called the Cram Chelate. But one thing we can quickly see is that now nucleophiles will prefer to attack on the left-hand side because that's the way that you can attack across the smallest group. And we can just see if we compare those two structures here, that the smallest group has moved from the right-hand side to the left-hand side. And this is quite a strong steric constraint. Putting in that chelating magnesium atom has made a 5-membered ring. And I can just draw this Cram Chelate out in a slightly different way to emphasize that. There's our 5-membered ring with our activated carbonyl group. And on that 5-membered ring, the hydrogen is going forwards and the phenol group is going back. Now this ring is pretty planar, so arguably the best way to describe what's going on here is that the phenol group blocks the back face pretty effectively when compared to how that hydrogen blocks the front face. So this is back to sterics again. Now I thought just to tie all of these ideas together, I'd show a particularly good example of this in natural product total synthesis. There are many examples. I've just picked a random one here of Preswinholide A. There's a key step that works really well using this key chiral aldehyde intermediate. Now we can quickly see that this intermediate has an alpha stereocentre next to the carbonyl. And we can also see that we'd expect the tack onto the carbonyl to go under Felkin-Anh control. I'll just draw the hydrogen explicitly. The hydrogen will be R small, the methyl group will be R medium, and this branch group here is much bigger. This will behave as R large. Now it's easy to get distracted by big molecules with lots of stereocentres, but actually the reactivity of this molecule is pretty boring. If we have a look over this end of the molecule, it's just ethers. It's inert. And this is part of the plan in the total synthesis, is to make sure we don't carry other reactive groups around when we want to do something to the aldehyde. So as part of the total synthesis, this intermediate was reacted with this allyl-silane in the presence of titanium tetrachloride at low temperature. Now we know that this is a Lewis acid, and also it's a potentially chelating metal, so we need to keep an eye out for that. We need to use a Lewis acid because an allyl-silane is not a particularly reactive species. It's not the best nucleophile in the world, so we need to give it a bit of help. We can note that at -90 degrees, we're definitely under kinetic control. And when we do this nucleophilic attack, we'll be forming a new carbon-carbon bond, so it's not a reversible step. For reference, this is known as a Saccharide Adolation. And this is the product that we're going to form. I've just truncated off some of the rest of the molecule down the bottom here. Don't worry about that. It's so far away from the reacting center that it won't have any influence on the stereochemistry of this reaction. The product that's obtained is this particular configuration of alcohol. It's claimed that this stereocentre is formed in 20:1 dr. Now this is excellent. That's actually a higher dr than you might reasonably expect for a Felkin-Anh controlled reaction. They're normally more in the 10:1 ballpark. But this system has been heavily optimized. And in fact, there's actually an extra bit of diastereo control coming from the beta stereocentre as well. To explain how this reaction works, firstly, I'm going to address the fact that there are some lone pairs on that beta stereocentre. But because there's a silicon group with some big bulky T-butyl groups on there, those lone pairs are not available for chelation. This is a well-observed phenomenon in protecting group chemistry, which is essentially what that group is doing here. However, I will note that on that beta stereocentre, it is a carbon electronegative atom bond, a CO bond, and we saw earlier that we have to keep an eye out for those. So let's just have a look at the Felkin-Anh model in this context. Here's my Newman projection of my aldehyde. Now, to get the weedy nucleophile, the allylsilane, to attack it, I need to have that activated with the Lewis acid, like this. The conformation that reacts has the hydrogen down here, the methyl group here, and our large branch group that has our beta stereocentre off in the perpendicular position. So this is the beta carbon. Now, this itself has 3 conformations, and it turns out that CO bond is being non-innocent here. There is another low energy conformation where the CO bond points in exactly this direction as I've drawn here. And that's because its dipole moment will oppose the dipole moment of the carbonyl most effectively when it's in this orientation. So this is the oxygen with the silicon on it and some other stuff. If we rotate this round, we can now see that the remaining stereocentres are like this. So there's just an R group at the back for the carbon chain and the hydrogen. Now, it turns out that this is really good because this conformation has put the R group out the way. What I'm describing here is the Evans polar model, which is a topic for another time, but these types of beta stereocentres can give rise to 1,3 anti-diastereoselectivity because of this effect. The Felkin-Anh model, though, is a 1,2 effect, which should be dominant over a 1,3 effect just because it's closer. So our nucleophile will attack across the small group like this, but the carbocation left behind from this reaction will be nice and stable. It's stabilized by the carbon-silicon bond that's next to it. So we get a really highly diastereoselective transformation here because we've got the Felkin-Anh model working really well. That will be the dominant factor, but also this molecule is set up to fit the Evans polar model, and the diastereoselectivity predicted by both of those models will lead to the same configuration of alcohol. This is a very useful idea to use in synthesis, the idea of matched reactivity. You don't want any other part of a molecule fighting against what you're trying to do. If you want to see more videos on this natural product type synthesis, I'm planning out a few at the moment, so please do let me know. If you found this video useful, please do give it a like and consider subscribing to my channel. And I'm just putting on the screen now a few other videos from my channel that might be of interest to you.